Hello everyone, welcome back to Spring Java Lab. In today's video, we're going to understand one of the most important features introduced in Java 8, the Stream API. If you've ever felt confused about methods like filter, map, sorted, distinct, or wondered what intermediate and terminal operations actually mean, then this video is for you. We'll learn each concept with simple examples and also discuss a few interview questions along the way. So let's get started. To save time, I've already created a simple product class along with some sample data. Each product has an ID, name, price, and category. Throughout this video, we'll use the same product list to understand different stream operations. Before we learn different stream operations, let's first answer one important question. Why did Java introduce the Stream API in the first place? After all, collections were already available before Java 8, and we could process them using loops. Let's say our requirement is to find the names of all products whose price is greater than 5,000. We don't need the complete product object. We only want the product names. Using the traditional approach, we iterate through each product, check whether its price is greater than 5,000, and if it is, we add the product name to another list. Let's run the program and see the output. As you can see, we got the product names exactly as expected. So, is there anything wrong with this code? Honestly, no. This code is absolutely fine, and you'll still come across similar code in many existing Java projects. But now imagine you're working on a large application. Today you need to filter products. Tomorrow you need to sort them. Then you need to convert product objects into product names. After that, maybe you need to count matching records or search for a specific product. If we keep writing loops for every such requirement, the code starts becoming longer and harder to maintain. That's where the Stream API comes in. Instead of focusing on how to iterate through every element, streams allow us to focus on what we want to achieve. Let's solve the same problem again, this time using the Stream API. Don't worry about these methods for now. We'll understand each one in detail in the next few minutes. At this point, I just want you to observe how easy this code is to read. We will get same result with this new code. But if you compare both approaches, this code is much more expressive. We start with the product list, apply the required operations one after another, and finally collect the result into a new list. Notice that we never wrote a loop ourselves. The iteration still happens, but it's handled internally by the Stream API. This makes the code cleaner and lets us focus on solving the problem instead of managing the iteration. Now we've seen why Java introduced the Stream API. But what exactly is a stream? So, is a stream just another type of collection? The short answer is, no. A collection, like a list or a set, is a data structure. Its main job is to store data. A stream, on the other hand, is completely different. Its main job is to process data. Think of a collection like a box of products sitting in a warehouse. A stream is like a conveyor belt in a factory. The conveyor belt doesn't store the products, it just takes them from a source, moves them through different machines to process them, and finally packs them at the end. Now let's relate this to the example we've been working on. Here, our product list is the collection. It already contains all the data. When we call the stream method, we create a stream from that collection. We can then apply different operations to process the data. In this example, we're filtering the products, transforming them into product names, and finally collecting the result into a new list. One important thing to remember is that the original product list remains unchanged. The stream only processes the data and produces the required result. Now that we understand what a stream is, let's explore the different operations we can perform on it. Broadly speaking, every single operation in the Stream API falls into one of two categories, intermediate operations and terminal operations. To make this super easy to remember, I've broken down their main differences across 5 key features. Let's go through them one by one. First is intermediate operators will always return a brand new stream, allowing you to keep modifying the pipeline. Terminal operators, on the other hand, break out of the stream hierarchy entirely and return a concrete result like a list, a primitive number, or even void. We can see this right here in IntelliJ. When I hover over .filter or .map, they both return a stream because they're intermediate operators. But when I hover over .toList, it returns a list string, making it a terminal operator. The second important point is execution. Intermediate operations are lazy. In simple words, they don't start working immediately. They just define the operations we want to perform. The actual processing starts only when we call a terminal operation. Let's actually see this lazy behavior in action. I'll make a small change to our existing example. I'll add a print statement inside the filter operation so we can see when a product is actually being processed. And for now, I'll remove the terminal operation, which is toList. Notice that we still have our filter and map operations, but there is no terminal operation at the end. Now let's run the application and see what happens. Nothing was printed. Even though we have written the filter operation and placed a print statement inside it, the code inside filter was never executed. That's because filter is an intermediate operation, and intermediate operations are lazy. They don't start processing the data until we provide a terminal operation. Now let me add to list again and run the program. Now we get the output. The moment we added to list, which is a terminal operation, the stream pipeline was actually executed. The third important point is chainability. Intermediate operations can be chained together multiple times because each one returns a new stream. A terminal operation, on the other hand, can only be used once at the very end of the pipeline. Let's see this in action in IntelliJ. In our code, we already have .filter and .map. Because they are intermediate operations, we can easily chain another intermediate operation, like .distinct, right after .map, to remove any duplicate product names. Now, let's see what happens if I try to add another operation, like .filter, after .toList. Notice that IntelliJ gives us a red compiler error immediately. It won't even let us compile the code. That's because .toList is a terminal operation. It closes the stream pipeline, so you cannot chain any more operations after it. The fourth important point is stream reuse. Once a terminal operation executes on a stream, that stream is consumed and closed. You cannot reuse it. Let's quickly see this in IntelliJ. I'll first create a stream from our product list and store it in a variable called product stream. First, I'll call count on our stream. This is a terminal operation, so it will consume the stream. Now let's try calling count one more time on the same stream. And this time, we get an illegal state exception. The reason is that the first count has already consumed the stream, so we can't use the same stream again. The fifth important point is the primary role of these operations. Intermediate operations are mainly used to process or transform the data. For example, filter can remove elements that don't match a condition. Terminal operations, on the other hand, are used to produce the final result. They can give us a result like a list, a count, a single element, or even a Boolean value. Now that we understand how intermediate operators behave, let's explore the most important intermediate operators you'll use every single day in Java. Let's start with filter. It takes a condition and keeps only the elements that match it. For example, if we only want products costing more than 5,000, we pass product.price greater than 5,000. Anything below 5,000 will be dropped. In our console output, we see only laptop and table, mouse, keyboard, and chair were dropped because their prices are 5,000 or below. Next is map. Map is used to transform each element. For example, instead of returning the complete product objects, let's get only their names. Here, each product is converted into a string, which is the product name. And in our console, instead of full product objects with IDs and prices, we get a clean list of product names. Next is distinct. Distinct is used to remove duplicate elements from a stream. In our products list, we have two entries for laptop. By adding .distinct, Java removes the duplicate and gives us only the unique product names. One important interview tip here, distinct relies on the equals and hashcode methods to check for duplicates. Since our product class is a Java record, Java handles equals and hashcode automatically for us. Checking our console output, notice that laptop appears only once now. The duplicate is filtered out, leaving us with 5 unique product names. Next is sorted. Sorted is used to arrange the elements of a stream in a specific order. If we don't pass anything, it sorts in natural order, but we can also pass a custom comparator. For example, let's sort our products by price, from lowest to highest, using comparator.comparing product price. So here in our console, we can see product with price 800, mouse, appears first, and products with price 65,000, laptops, appear last. Next is limit. Limit is used to truncate the stream so it returns no more than n elements. For example, if we only want the first 2 products from our list, we can attach .limit, 2. And if we look at our console output, we see only 2 items, laptop and mouse. Even though our original list has 6 products, limit stopped the pipeline after processing the second element. Next is skip. Skip does the exact opposite, it ignores or discards the first n elements of a stream and processes the rest. For example, if we pass 2 to .skip, Java skips the first 2 products and starts processing from the third product onwards. Checking our console output, notice that laptop and mouse, our first 2 items, are completely gone. The list starts directly from keyboard, followed by chair, table, and the second laptop. Finally, we have peek. Peek allows you to inspect elements as they flow through the pipeline without modifying them. It's primarily used for debugging and logging. For example, if we place .peak between filter and map, we can log each product that passed our price filter. In our console, you can see our peak log printing each matching product object right before it gets transformed into a string name by map. Now that we've covered the important intermediate operators, let's move on to terminal operators. Unlike intermediate operators, terminal operators produce the final result from our stream. Let's look at the most commonly used terminal operators with some simple examples. Let's start with toList. We've already used this several times in our examples. toList collects the elements from the stream and returns them as an unmodifiable list. For example, let's get the names of all our products and collect them into a list. In our console, we can see a list containing all the product names. Next is forEach. Unlike toList, forEach does not return any value. Its return type is void. forEach is used when we want to perform an action on every element of the stream. For example, let's simply print the name of every product. In the console, we can see the name of every product printed on a separate line. So here, we're simply performing an action for each element instead of collecting a result. Next we have count. As the name suggests, count simply tells us how many elements are present in the stream. For example, let's count how many products cost more than 5,000. In our console, we get the result 3. That's because we have 2 laptops and 1 table with a price greater than 5,000. Next is findFirst. findFirst returns the first element from the stream. Let's say we want to find the first product whose price is less than 1,000. In our case, the first matching product is mouse. We also have findAny. findAny is similar to findFirst, but instead of asking for the first element, it can return any matching element. So let's use it to find the product whose price is greater than 5,000. With our sequential stream, we will often see laptop because it's the first matching element. But findAny doesn't guarantee that it will always return the first element. Next we have AnyMatch. Instead of returning a product, AnyMatch answers a simple yes or no question. Does at least one element match this condition? For example, let's check whether we have any product costing more than 60,000. In our console, the result is true, because we have a laptop costing 65,000. AllMatch asks a different question. Do all elements match the condition? Let's check whether all our products cost more than 1,000. And the result is false. That's because our cheapest product, the mouse, costs 800. So while AnyMatch checks whether at least one element matches, AllMatch checks whether every element matches. And finally, we have NoneMatch. It checks whether none of the elements match the condition. For example, let's check whether we have any product with a negative price. In our console, the result is true, because none of our products have a negative price. Now, there is one more critical detail about intermediate operators. They are actually further classified into 2 categories, stateless and stateful. Let's break down the differences point by point. First, let's look at how they handle elements. Stateless operators process each element independently. They do not need to know anything about the other elements. On the other hand, stateful operators must retain memory or a history of previously seen elements to do their job. Moving to our second point, let's compare their execution. Stateless operators execute as on-the-fly streaming. The elements just pass right through one by one. However, stateful operators must inspect prior or all elements before they can move forward. Finally, let's look at some examples. Common stateless operators include filter and map. Common stateful operators include distinct and sorted. This makes perfect sense because distinct needs to remember what it has already seen to remove duplicates, and sorted needs to gather every single element before it can put them in the correct order. Now that we understand the Stream API, its intermediate and terminal operations, and how they work together, let's try to solve some common Stream API interview questions. Let's start with a very common one. What's the difference between map and flatMap? We've already seen map earlier in the video. We use map when we want to transform each element into something else. For example, we converted each product into its product name. But let's consider a different situation. Suppose we have a list containing multiple lists. So our data looks like this. Now, let's first see what happens when we use map. In our console, we still get the nested structure, so map has transformed each element, but the overall structure is still a list of lists. But what if we don't want this nested structure? What if we want one single list containing all the values? That's where flatMap comes in. Now let's check the console. We get single list containing all the category. So what exactly happened here? flatMap takes each inner list, converts it into a stream, and then combines those streams into one single stream. So from list of string, we end up with list of string. And that's the key difference. Map is generally used for a one-to-one transformation. FlatMap is useful when we have nested data and want to flatten it into a single stream. Now let's move to our second interview question. Find the second highest priced product. Pause the video and take a few seconds to think about how you would solve this using streams. One simple approach is to first sort our products by price in descending order. Let's understand what's happening here step by step. First, sorted method looks at the price of each product and arranges all the products from the highest price to the lowest price. So the most expensive product comes first, followed by the next expensive product, and so on. Once the products are sorted, the product at position 1 is our highest priced product. But we don't want the highest priced product. We want the second highest one. That's why we use skip 1. Skip 1 simply tells the stream to ignore the first element. So now the highest priced product is skipped, and the stream starts from the second product. Finally, we use find first. Since the stream is already sorted and we've skipped the first product, the first element we find now is exactly the second highest priced product. Now let's move to our third interview problem. Find the names of the top 3 most expensive products. Take a few seconds and think about how you would solve this using streams. One simple approach is to first sort the products by price in descending order, and then take only the first 3 products. Let's understand this step by step. First, sorted arranges all our products based on their price. Because we're using reversed, the order is descending. So the most expensive product comes first, followed by the second most expensive, and then the third most expensive. Next, we use limit 3. This tells the stream that we only want the first 3 products from that sorted result. So after this step, we have our top 3 most expensive products. But the requirement is not to return the complete product objects. We only want their names. That's why we use map. Here, map converts each product object into its product name. Finally, toList collects those 3 names into a list. Let's check the console. We can see the names of our top 3 most expensive products in descending order of price. Now let's move to our fourth interview problem. Find the most expensive product from the electronics category. Take a few seconds and think about how you would solve this using streams. One simple approach is to first filter the products by category and then find the product with the maximum price. Let's understand this step by step. First, we use filter to keep only the products that belong to the electronics category. So products like chair and table are removed from the stream because they belong to the furniture category. Now our stream contains only electronics products. Next, we use max. We tell max that we want to compare the products based on their price. So Java looks at the prices of all the remaining electronics products and finds the one with the highest price. Let's check our console. We get the laptop with a price of $65,000. So these 4 examples show an important point about the Stream API. It's not just about knowing what filter, map, sorted, or find first do individually. In real applications, and especially in interviews, the important part is knowing how to combine these operations to solve a particular requirement. Once you understand how the stream pipeline works, these kinds of problems become much easier to approach. And that's where we'll wrap up today's video. If you found this video useful, you'll find the source code and more Java and Spring articles on my website springjavalab.com. I've added the link in the description. I'll also be covering more Java and Stream API topics in upcoming videos, including some more advanced interview problems. If there's a particular Java or Stream API topic you'd like me to cover next, let me know in the comments. Since this is a new channel, your suggestions are genuinely helpful in deciding what to create next. And if you found the video useful, consider subscribing to Spring Java Lab for more practical Java, Spring Boot, and backend development tutorials. Thanks for watching, and I'll see you in the next video.